I'm Andrew. I'm a Principal Solutions Architect at AWS. I effectively spend my time talking to public sector customers mostly, but practically anyone will listen to me waffle on about things I find interesting, which can be anything from this through to all sorts of weird and wonderful topics. So come chat afterwards. My badge says I don't want to talk about US East 1. I will if you want to. I won't tell you anything more than you already know on the internet, so it might be a bit fruitless. We can go from there. Yeah, as John mentioned, I'm going to talk a little bit about a thing called Nitro, which is a feature, a thing we have. It powers practically everything you do in AWS every day, but you'll probably never come across it. It's a transparent layer at the bottom, which is particularly important. Thank you, sir. Particularly important for effectively getting things to work. So, first and foremost, I apologise for Monday. If you've not had that already from us, that was an issue. Health.aws.amazon.com has a bit more of a run through about what happened if you're interested. There will be more stuff up there, I'm told, in the next few weeks. So take a look at that. Like I said, things happen. I was thinking earlier on, we used to have outages in on-prem systems probably monthly. Everyone just sort of got used to it. The collective memory's forgotten that. Now when they happen every 4 or 5 years, it seems that that's the big thing. It is, if you can't make a streak on Duolingo, if you've lost that streak or you're risking it, I can totally see why it's a big issue. But we've gone past the point where on-prem systems fail every 2 weeks. So I think once every 4 years seems a bit more reasonable. Right, let's start here. So, innovations in silicon. Surprise is what I titled this slide, and I thought it sounds a bit too new wave, avant-garde 80s band, but I kept it in there because why not? And what I want to start talking about to begin with is how we build our silicon and why we build silicon in the first place, and what that means and how we get there. So this is the starting point of the history about Nitro, and we'll get to what Nitro is in a second. I've not forgotten that part. I'm going to give you the background first, and we'll get to the what is it next. So we've built chips in silicon in multiple areas to begin with. Nitro, which is the most widely used today, and we'll come into that a little bit more, but effectively Nitro is our hypervisor. It's a combination of an actual software hypervisor, because it's not physical, but there we go. Software hypervisor, Nitro cards, which are physical components, and then a variety of things to do with storage, network, SSDs, and security, which we'll talk about in depth in a few minutes. We started that in 2013. That was started back with the C3 instances, I think, when they got enhanced networking was a feature that came out. And we'll talk about how we get to that in a minute or two, but that was the first time we came across this idea of Nitro and when we got to it. And we started working with a small startup at the time called Annapurna, and a couple of years later we acquired Annapurna, and then Annapurna now produce all of our fabs and produce all of our silicon for us. So that's where we started there. We also have other types of silicon. We've got Graviton, which provides the best price performance for general purpose workloads. Customers run the majority of compute in AWS on Graviton instances today. So you might think Intel instances still rule the roost, for example, or AMD or whatever. Nope. The vast majority of AWS's customers who run general purpose workloads run on Graviton, largely because it's cheaper and it performs effectively the same function for 90% of use cases. And we've also got specific chipsets for specific types of use, two of which are Inferentia and Trainium. Inferentia, you may have guessed, does ML inference, and Trainium does ML training. I am trying not to say the other two letters that this industry is so enamored with right now. So we'll use slightly backwards terms for it. So that's what we do in silicon from a high level. You might be wondering, well, why do we bother in the first place? And so the first reason we do all this and build our own chips is for specialization. When you're running an infrastructure as big as AWS, which is big, then fundamentally you hit weird and wonderful edge cases left, right, and center. Our needs are not needs you could probably usually ever come up with in terms of size, scale, reason, need, etc. We come across weird things all the time. One of my favorite things I like to say is that when people say, oh, it's a 1 in a million or a 1 in 10 million time issue type thing, and you're never going to come across it in real life, that means that for us it happens probably about 5,000 times a minute. 1 in 10 million chances happen really, really, really regularly for us. So for it to be rare for us, we're probably talking 1 in the X trillions or X multiple trillions of times. So we get to start by specializing with we build our chipsets, we get to start with specialization, and we specialize that hardware for our own big scale use cases, basically. We tailor designs for operating in and on us, but the other thing we do is we also remove features and crap, quite frankly, that people don't need from chipsets that we could get from vendors who might want that chipset in there for their own reasons. We don't need that stuff, let's get rid of it. That allows us to turn around and say, well, there's more compute power effectively in those chips now that we can use for features that people actually want to see. And if they don't want to see any more features in them, that's great. We've still got more ability to use chips more efficiently. We can fit effectively more physical chips to more instances. One nice thing it does, it also reduces our power efficiency as well. If we're only using chipsets for things that actually are needed, we need fewer chipsets. If we can get to fewer chipsets, our PUE equivalent goes through the roof, which is good. Another reason we build our own chips is for speed. Fundamentally, we own the end-to-end development of everything we do in AWS. So we own the entire supply chain, we own the land, everything. We own the fences, we own practically everything you can think of in terms of how you would build and operate a large or very large hyperscale infrastructure. We define what that product might be in the first place. We design it. We do everything end to end. We're not reliant on somebody else to do it for us. And if we were reliant on a third party for silicon, that would be a fairly large area that we're not really getting to impact as much as we would be able to. It's also more costly. We can do things cheaper if we own the end-to-end process. Turns out one of our sister organizations also owns a very, very, very extensive and pretty quick logistics network, which also helps an awful lot as well. So we shrink effectively the time from concept of an idea to deployment to much quicker than we could do through anything else. And we also own the full integration of how our software works with our hardware. So there's no back and forth about our software is written for this and the hardware vendor says that, and there's none of that. It just happens. It just works. Other thing we can do is we can innovate a lot quicker as well. So teams at Amazon are able to go and talk to other teams quite quickly without having to go through a third party to say, look, I want this feature, I want that feature. It ends up on some third party's backlog. It never gets done, all the usual stuff. That doesn't happen. We can innovate much quicker, and we can also turn around and say, well, the infrastructure that we've got today, we want to get to this point in future. How do we get there? We're going to pull in this team, this other team, wherever it might be involved to get to a point where everything is able to be delivered. We're not reliant on other people's organizations and priorities to continue. And finally, a big one for me and for us is Nitro. Is security. It provides a mechanism to enhance the security of the infrastructure that you run on every single day. So we can turn around and produce great features and turn around and go, yes, we can meet the following new weird and wonderful security needs, because it gives us a much more simple, as we'll find out in a minute, layer to start building upon. The foundations are a lot firmer. And some of the ways it does that, which we'll discuss in a minute, are things like a hardware root of trust in every single physical server in our data centers. There's verification of the firmware on the server when it boots, and in some cases of your EC2 instances, and there's no human access whatsoever to EC2 instances or the infrastructure they run on in most cases. So let's have a look at how this works. There are sort of multiple layers to this. We have Nitro at the bottom. That's the bit we're talking about today, and the hypervisor on top of it. We will touch sort of on the bottom two squares are there, if you will, and we'll divide that up into the three areas of storage, networking, and security. The instance OS and the application, fundamentally the stuff you work on every single day. So that's the top end stuff is the thing you choose every day. The bottom end stuff is the stuff we produce to make your stuff work. That's the way to think about this. Hi. Sure. Cool. So, we started Nitro with a fairly simple question, which was if we applied all the learnings from having run the Zen hypervisor for many years, and we put them all together, and we said, how would we change how we run things today? That's a big question for us because it impacts all sorts of people. It impacts what, for example, the people who work in our data centers do every day. It impacts their processes. It impacts our ability to deliver the same availability and uptime. It impacts the ability to deliver security features that people want. It impacts all sorts of stuff. And so lots of suggestions came out of that. Performance features were lots of things that people wanted regularly. People wanted a load of new security features in a variety of means and manners. And fundamentally, those things are listed there. People wanted better throughput, a simplified hypervisor, reduced latency and jitter, and bare metal instances, which was a big one for people who didn't want to run things that we couldn't run because we had a hypervisor sat in the way that wouldn't let you run things. So that was that part. On the security side of things, people wanted transparent encryption for all their disks rather than just relying on things like, for example, TDE in Oracle. We wanted a hardware root of trust. We wanted no operator access, which is a big one for us because we don't really want to touch your data at all in any way, shape whatsoever. Like that should be your data, not ours. It's a big thing for us to earn trust by doing that. And we wanted narrow and auditable APIs. APIs that are big in scope are a problem for us because they can be misused. So therefore we have to put lots of mitigations in to prevent the misuse. If we can turn around and have an API that is narrow in scope and still auditable, then we don't have to put as many protections in place because the scope of the API is significantly limited to begin with. So we could have taken the hypervisor we used to use, Zen, which I alluded to, and we'll talk about how this happened in a minute, and try to change those, but Zen has some fundamental design problems which at our scale we weren't quite happy with. So we decided, let's see if we can fix them as a project. And fundamentally, this is how Nitro was born, by trying to answer that question. So the Nitro system as a whole is sort of 4 things together. It's purpose-built hardware and software. We've long built our own hardware and our own software. So that's the purpose-built side. We've been doing that more since 2013. So what's that, 12-ish years ago now, when we started working at Annapurna and then later acquired them. The big one, as I mentioned earlier on, was the C3 enhanced networking feature for C3 instances, which came about, which gave you effectively higher performance and higher bandwidth, lower latency, and the same price. Then we introduced Nitro as a concept, rather than just being enhanced networking in 2017. And now we've got 5 different generations, at least, of custom chips which run on Nitro. Most instances you should be using, in fact, every instance type you should be using should be running on a Nitro hypervisor. If you're still running on a T2 micro, please stop and go and do something else. Like, that should be fixed tomorrow morning. We've expanded it to other I/O with newer Nitro cards, so we're not just talking about things like storage. We've also been able to enhance it in different ways, and we'll get to one of my favorite interesting parts towards the end. But we've been able to turn around and say we actually need to access things in hardware, but we can do that in a much safer, much better, more consistent way now through Nitro and the design patterns it gives us. And fundamentally, we got to remove a bunch of stuff we didn't need from our instances and put stuff in there we do need, which is sort of the third point there. We built it for ourselves because our customers wanted stuff we could otherwise not deliver as easily. Today it powers over 500, I think it's actually 750 at least different instance types, so the vast majority of stuff you can run in EC2 runs on Nitro. Like I said, if you're using your T2 micros, please stop. Right, so back in the day, this is effectively, from a high level, what an EC2 droplet, as we call it, a server in the rest of the world's terminology, would look like. And effectively, we'd gone onto the Zen website and downloaded a copy of the Zen hypervisor. That was basically what we did. And you'll see a couple of things there that are happening. So we have instances at the top. Those are the things you produce every day and instantiate every day that fundamentally run an EC2. But as you'll see, they're one of a number of components inside that to actually work. We rely on a huge amount of other foundational stuff in order to get those instances to work. We have the hypervisor in the middle, Zen. And then we have this weird thing to the left called DOM0, which, if you're not used to it, DOM0 is effectively a guest virtual machine sat inside a hypervisor that effectively tries to provide translation between hardware and software. And it provides, in our case, it provided access to a VPC for networking, provided access to EBS, to local storage, and to management, security, monitoring, and all the other bits of useful stuff that are good for us to know about our droplets, but also power things like CloudWatch occasionally and other bits and bobs. One of the big problems we've got is that Zen's great, but it does an awful lot of stuff. And it's a bit of a, the more it does, it's a bit more of a powerful thing that is a bit too powerful in certain circumstances. So Zen's good for things like memory management, CPU scheduling, device emulation, limiters. It will do things like enforce security groups from instances to make sure that traffic is going the right way, and so on and so forth. But the big problem for us is fundamentally DOM0 runs as root. And as a result, if I get into DOM0, I have effectively free range over whatever the heck I want down at the bottom end, which is not ideal. If you've built a load of protections into your instances to stop that, we just basically open a big bypass through the middle of it. So we didn't really want that to happen. One of the weird things about DOM0 is it also has a full-blown Linux user space inside it for some reason I can't quite fathom, if I'm honest with you. So you could actually theoretically have run things inside DOM0 that were not belonging to customers at all. That was a whole new layer of stuff could have run in there, and that wasn't great from our perspective. Stuff shouldn't be running there unless it's in an instance in the first place. So we decided, can we start to offload that stuff onto hardware devices? We prefer hardware, we know how hardware works, we can touch hardware, it's much nicer in some ways. And we started that with networking. So we took away networking, and we started that with Nitro cards. So Nitro cards are physical cards. There's a family of them. They run across different chipsets now, and they physically exist. And we started off by offloading the I/O functions of networking, or of VPC in our world, to it. It works over PCIe. If you plug it in, you see some ENA devices attached to the device, and effectively the instances see that and know where to route traffic to. It acts much like, in a very simple terms, much like the NIC in the back of an instance or a back of a machine in the first place. But the good thing is it takes all the responsibility for networking off the CPU in the first place. So we've got less stuff running in the CPU, more running in something dedicated to it. We've got much more control over what goes where and how things run. So first thing we can do, we can take all that stuff off the CPU on the host. We can take ENI attachments off, security group management off, flow logs, routing, limiting, DHCP and DNS can all go. That lot is, it seems not an awful lot there necessarily in terms of how much CPU time would be spent processing that stuff, but it's a fair chunk of stuff. So we can take all those pretty fundamental and important things off an instance and off a host CPU and put them more in towards the hardware itself to get processed there. We can do things like encryption at the VPC level. So we can turn around and go, I want AES 256-bit everywhere. We can do that now because I've got a physical card responsible for that without the huge overhead on top of the CPU that's happening in the host. And we can enable features like Elastic Network Adapter, and ENA Express and a variety of other weird and wonderful networking features that you probably really only use if you're doing HPC. So that enables us to do other things as well. So one of the nice things about ENA is we can turn around and scale up our capacity for bandwidth significantly more as well. So we can go from things like offering only 10 gig a second, for example, to 25 to 100 to 400 to, there might be something with more than 400 gig a second now, but definitely up to 400 gig a second available in some instance types. So we can keep doing that and so on and so forth. And as the world continues to demand more and more bandwidth out of things, I think we'll either get to a point where we start offering more than 400 gig a second, we'll get to whatever's next, and so on and so forth. So that one chipset design and that one idea of moving all this stuff to hardware and into cards actually provides us an awful lot of advantage at this point. We also built the thing called the Elastic Fabric Adapter. So this is how we do all the stuff, the really high-end stuff in HPC, which I'm not an expert in, but it uses things like the other AWS ideas that were designed, like SRD, which is a datagram processing situation for networking stuff effectively. So it enables us to do proper low latency at scale and to do multipathing as well. For the average user, however, the big reason that we do all this, and the big thing you'll notice, is that we can go from a sort of baseline down the bottom, 2006 early days of 1 gig a second, and you can see, we started to playing around with the idea of Nitro in about 2013. And as we go through, we get to 25 gig a second, which I think was probably around the same time we started to do start to add more features onto the enhanced networking stuff. And then we started to do some more stuff with the network to get to 200 gig, and then we've gone up and up and up from there. And my 400 gig thing is obviously well out of date because apparently we're now on 6.4 gig a second. So there we go. So there's networking advantage. There's also storage advantages as well. So people really want to make sure their networks are performant, but fundamentally your network can be performant. You can get more requests in, you can do bigger requests, that sort of stuff. But if your storage isn't as performant, you're going to hit a bottleneck there instead. So we built another Nitro card. This one's for storage. It looks different to the networking card because it does a fundamentally different job. The only shared bit really is how it connects into the rest of the host over PCIe. And it provides us with effectively exposing NVMe interfaces so that you can get two main advantages: better storage bandwidth out of the card, so better storage bandwidth onto EBS volumes, but also it makes life a lot easier for those people who have weird and wonderful storage needs, because we then now support NVMe natively effectively through the wide variety of standard drivers out there for it. We also have advantages on the EBS data plane. So the EBS data plane is where your stuff is stored. The control plane is what controls this whole day. It doesn't store anything there though. So the data plane has advantages. We've got better support for encryption, and we could do transparent encryption, and we could do that in physical memory at that point. But we could also use NVM to get to remote storage protocols as well, and a variety of things that if we did them on the host in the first place would just add too much CPU overhead. And much like the last slide we have down here, we were sharing initially. So back in the day in 2006, 7, 8 area, we were turning around and saying that the network bandwidth was shared with the storage bandwidth and everything else was going out through the same NIC. So if we've only got a gig NIC in the back of an instance, I've got a gig to surface everything. Whereas when we start taking that out and getting dedicated EBS bandwidth, we can start to see we go up from having a gig of dedicated EBS bandwidth, 2 gig, 4 gig, 14, 19, so on and so forth. And you'll notice the number of IOPS increases exponentially with at the same rate as well. So it gives us a much better way of scaling the performance of EBS. So let's dive a little bit into what happens below the storage card. We also have the idea of Nitro SSDs. And Nitro SSDs are not just normal SSDs, because we also dislike the idea of an SSD and how most are designed. A traditional SSD looks like this. You have the data is actually stored in a thing called a NAND, which is basically a not AND gate effectively, or your data is stored in one binary, and it's either an individual bit is either NAND or not, effectively. It's how things work. And then we have a thing called a flash translation layer at the bottom, which helps to map things on disk to logically to where they need to be, and does some stuff like garbage collection and manages wear leveling and various of the low-level storage stuff, which again I'm not an expert in. So that's how most SSDs are produced. If you go and pick one up from your favorite online retailer, one will come in a small grey-looking plastic bag like that, NVMe and PCI bus on the end, and that's how they are. The problem, well, one of the problems with this design is in a NAND, you can only erase megabytes at a time because of how they are. So if I want to take a big object and chuck it onto an SSD and it gets stored in one NAND, for example, I can only delete that big object megabytes at a time. But if my object is many hundreds of gigabytes, I'm a bit screwed. I have to wait until that whole thing can be done, which can take quite some time to delete objects and delete things. If you want to update 1 byte, you have to copy the data to a brand new location. If we take a simple example and say that each of these NAND squares on there, which there are 8 of them, are 1 gig each, and I have a 1 gig object or 1 gig file, I have to make a change to that 1 gig file. I have to copy the file first to another NAND, make my change before it gets written, and then once I'm happy with that, then delete it from the original NAND in the first place. So 2 problems. 1, it's slow. Doing that whole process is slow. 2, I have to effectively copy a file twice, use up twice the amount of storage space on there, and twice the available amount of NAND on that storage space on there, and then I can free up that space again, which is really inefficient, and at our scale is huge amounts of wasted volumes every day. So now each manufacturer produces their own SSDs, and each vendor has their own FTL, the bottom layer that does all the sort of logic behind the SSD, and they do that with their own APIs and all the rest of it, so that if I go to one manufacturer and go to another manufacturer, the 2 actual low-level concepts are going to be completely different, even though fundamentally it's NANDs and FTLs. Again, a bit of a nightmare for us. If we're trying to rely on someone's supply chain and we need to get X from one vendor and we've exhausted their supply chain and I need Y from another one, my system has to be able to cope with all these different permutations of different vendors' SSDs, which is a nightmare. In some vendors of SSDs, you will find that some of their product families work in one way, other ones work in a completely different way, even though they were produced at around the same time. It makes no sense whatsoever, but that's what they do. You can see 6 common examples of SSDs from well-known SSD vendors there. They all look different. There's no real fundamental good reason for that, aside that's how they think, that's how they do things. The way to think about the differences in SSDs is thinking like databases. Fundamentally, we need to store some data in there, but each individual SSD looks, acts, feels, is different in the way it works. It's got different concepts, it's got different understandings of things, it's got different logic, it's got different everything. And they're all a pain for us. So, one of my favorite parts about this is that on a number of SSDs, garbage collection can just occur randomly. You have absolutely no idea. It doesn't happen at any particular point. It just occurs at some point. So you'll be like using an SSD and suddenly be like, oh, sorry, performance is gone. Garbage collection time. That could happen 4 times in a second and not happen for another 3 weeks. Like, just a thing. So, we don't like those. We didn't like the idea of those, but we still need them at the end of the day. You need to store some stuff somewhere. We need to have a data plane for you to put your stuff in EBS. So we decided we're going to take the flash translational layer and stick it into a Nitro card instead. So we're now responsible for the translation. We're doing the sort of API calls between our instances in EC2 and into EBS. That's now our responsibility. 3 main things it does. Firstly, it reduces latency by about 60%. So we get 60% instant performance increase if we take the FTL out the SSD and give it to ourselves. It improves the reliability of the whole system end to end anyway. Effectively, that's because of a lack of writes or lack of reason to need an FTL on a heavily written device. And then thirdly, we can encrypt all the data on there with an ephemeral key, because now it's much easier to do that. We have more control over the FTL, which means we can put the key in the FTL and manage it through that way, rather than having to manage that on lots of different SSDs and how they work. So And we can encrypt all the data with AES 256. We also get things like faster firmware updates, and yeah, like I said, 60% lower I/O latency. So just by taking that one reasonably small component out, chucking it ourselves, we're now getting a lot of advantages out the back of it, which fundamentally really means better performance for you, usually cheaper prices. So, on this slide here, we've now taken the idea in the host CPU, the one we had earlier on, we've now taken away local storage and EBS storage are managed by the same card, and VPC networking. So we've got two cards here managing all three of those things. Problem is I've still got a DOM 0 because I've still got management needs, security needs, monitoring needs, all the rest of it. And what we'd like to get rid of is that big Zen thing in the middle. But we can't do that when we've got a DOM 0, and we can't move the DOM 0 until we got rid of that pink square at the bottom right. Which leads us on to our next layer, which is the Nitro hypervisor. So Zen's a hypervisor, it runs in software. Nitro has a hypervisor that also runs in software, but it's taken all the stuff out of it because it's no longer responsible for doing anything like managing PCIe access or anything like that, because the cards are doing it. So now we can get to a point where we've got a really lightweight hypervisor responsible for doing the bare minimum, and at the same time we can get a hypervisor to do the things it should be doing, like effectively memory and CPU allocation, because they are good tasks for a hypervisor to do. It also means we can do things like get bare metal-like performance. So that's where we get our bare metal instances in EC2 from. We can install any operating system you want on top of the Nitro hypervisor, in theory, and it'll give you bare metal-like performance. We say like, it is indistinguishable in most use cases from bare metal. There will be theoretically a slight overhead because there's a hypervisor in the way, but for 99% of use cases, you're not going to notice that. The number of people I know running bare metal instances is also super low as well. So it's a niche thing, but it's now doable, which is good for some use cases. One other great thing about the Nitro hypervisor being lightweight, because we removed all the stuff, is there's no SSH, there's no systemd, there's no networking stack, there's none of this. So fundamentally, the thing's now completely uncontactable unless you've got a good way into it in the first place, which we designed for our own needs only, not allowing anyone to get into the thing. And then we've got another bit of another chipset on there called the Nitro security chip. So the hypervisor works together with the cards and the security chip, and the security chip is integrated directly into the motherboard. So from the very moment that motherboard is fabbed in the first place, it basically traps I/O and it puts into non-volatile storage, and it acts as a hardware root of trust. So we use that for two main reasons. One, we can provide security advantages to your instance and your data. So one of the recent features we announced was you can now prove you can now verify effectively the attestation of your instance in the first place. So if you want your instance to look like A and you want to prove that cryptographically, you can now do that. Behind the scenes, that little chip is doing all that for you. That's how that works. But the other advantage it provides is a hardware root of trust. So when the droplet spins up in the first place, or an instance spins up in the first place, which happens all the time in our world, right? Droplets fail, things fail all the time, as you found out recently. We can turn around and go, do we think that that droplet is actually running the software it should be running in the first place? And if it's not, or we don't think it is, or we haven't got cryptographic evidence that it is doing, we completely kill the droplet, we basically take it out of service, it gets put to one side effectively, we spin everything up on a next droplet available to us, and we just continue on and keep going there and there. When we need to, we'll go back and fish that old droplet out that's now looking a bit iffy, and investigate it or scrap it or whatever, and it'll come out of the data center in little small tiny little pellets, and we'll use that to get recycled or whatever happens with us. So the way we do this is in the Nitro security chip is we measure the contents of flash devices that exist on the motherboard. So we turn around and we go to the motherboard, can you measure all the contents of everything on your flash devices that are connected to you? And we get a series of results back, a number if you will to express it that way. We then confirm that that matches the expectation or is in range of the expectation. And if it doesn't, or it's not in range, then we effectively turn around and go, that droplet's not useful to us anymore, bin it, get rid of it, do whatever, move all your processing and all that onto another droplet. Now you might not see this happen as much anymore, but back in the day you used to get instance retirement notifications, and effectively one of the reasons that would happen, not the only reason, by far not the most common reason, was that we didn't trust the droplet for whatever reason, largely due to that process in this specific example, and we're saying don't run the compute there, we're going to run it elsewhere instead, and we're letting you know that we're going to shift your compute. There might be half a nanosecond of downtime that you frankly probably won't notice, because by the time you've logged in with SSH, I think it'll be back up anyway for the daemon to have responded. So we're there. So that means fundamentally that chip alone means we can run we're running the firmware we expect. Everything's nice and safe. All the guarantees and the good things we say to you about where your data is and how it's secured and all the rest of it can be met. because we can prove it. So once we've moved that into the hypervisor, we're then left with a host CPU, which has some customer instances. Zen is a big hypervisor. DOM0 running as a sort of translation layer, if you will, a bit like the hypervisor version of the FTL from the SSD world, which runs as root and is still a colossal problem at this point. But all the actual talking to hardware is being moved out to the Nitro card, or Nitro cards. So you're getting all the great advantages of things being moved to hardware with all the risk of all the stuff still running in software, which is not a great position to be in. So then we can do this. We can bin that, and I think we can bin, is that right? Yes. We can bin that as well. So now we're left with host CPUs that just literally run customer instances and a very lightweight hypervisor. And that very lightweight hypervisor is responsible for talking to these 4 main areas and other things as well. You get all the performance and security enhancements and cost effectiveness effectively from us moving to hardware, which we can have a much better control over than if they're in software running in the Zen hypervisor. That means that the host CPU now has freed up resources. We can put more instances on there. Things get cheaper, things get easier, things get whatever we can do with that. We've got more space, if you will, more processing capacity to put new instances onto things. We get bigger instance types. And fundamentally, that's how we get to that. So the rate of new instance types from 2006 to 2017 definitely grew, but nowhere near as much as 2017 to 2023. So in the first 6 years, we grew a bit. In the next 6 years, we grew significantly more. Whatever the delta between 70 and 750 in terms of order of magnitude is, but it's large enough, right? It's at least 10 times. So today, that is... it took us 11 years back in the day to grow from 1 instance type to 70. And as you can see there, we got to 6 more years to get to 750 from that. And we keep going as well. There's probably more than 750 nowadays, some of which you just shouldn't use. T2 micros, no, please stop. But we've got to that point. We will get to 1,000 at some point, probably this year, maybe next year, I don't know. ET2 just keeps rolling instance types out. We will keep getting there. But we couldn't have done all that and increased all that unless we had all the stuff I've just mentioned. So that leads us to our third part, which is all about how do we keep our customers' workloads secure and confidential. Because fundamentally, if you don't trust us in the first place to do that, you won't use our services. That's not having a business. Like, this doesn't end well. So, as you'll know, we've got a shared responsibility for security. We'll take responsibility for the stuff that we control, the cloud bits in that model, if you will. And that involves things like our physical facilities, the fences, the staff, all the stuff that you don't touch and see that has to exist physically for the stuff that doesn't exist to work in the first place. But you're responsible for security in the cloud. So that's all the stuff that you're like patching of your operating system, security groups, logging, all this stuff you do every day, especially in EC2 land, to operate. So like there's a couple of examples down there: VPC security groups, encryption, management of credentials, OS, applications, all the rest of it. Now, one of the things about shared responsibilities for security, and specifically how we've moved to a Nitro host now with a Nitro controller and the Nitro cards and all the rest of it. The Nitro controller, by the way, is a new concept on this slide. You're not missing whole slides. The Nitro controller effectively provides a nice, easy translation and communication layer into the Nitro card, so you can get through to the host. We'll see why that's important in a few slides. But one of the other things about this is that the older instances do, if you're still running them, still provide the same things we say they do. That hasn't changed. Nitro just makes life a lot easier for us and for you. So you should move to use Nitro instances. But if you are running instances that are not on Nitro and are still on Zen-based hypervisors, the same things we say about those instances and have always said about those instances still holds true. It's not as if we moved focus to touching onto Nitro and ignored all our responsibilities for Zen stuff. There's just a lot less of it nowadays. So one of the things that having our own security chip in there and a hypervisor that's lightweight and all the rest of it allows us to do is to answer, how do we manage confidential computing? And confidential computing effectively is, how do I break down the trust I have to have between my EC2 instance with whatever I'm running on that and the fact that a cloud operator who I don't necessarily know or have an in-depth detail of their processes, how do I basically break that required trust? I don't necessarily trust this cloud operator in a model of confidential computing, but I do need to use at EC2 instances because that's where my strategic direction for compute has gone. And inside that EC2 instance as well, how do you break down the application or the bits running on that, the things that are actually confidential from the things that are not? Now, for many years, file systems have provided us ways of doing that in various different ways. And you could probably do that for some of your stuff there, but there are a number of use cases where fundamentally that protection is not sufficient. So we wanted to work out how can we provide an answer to this. Industry-wide in the confidential computing space, that's called Dimension 1. I'm not sure if there's any other dimensions. I've never come across any of them. I don't know why it's called 1 and not 0. Who knows? These are the big questions in life that I just can't get answers to. The other one is, why there's no Iron Brew in London? Like, that's the thing. Like, I can't find any. It's annoying me. Anyway. So we wanted to provide physical separation between where the code that you provide every day is running on a host CPU in an instance and where our services run the Nitro cards. The two things are required of each other. No point having Nitro cards without an instance, and your instance won't boot up without a Nitro card. So we can't fully get rid of them entirely. But what we can do is try to enforce some proper separation between things and get proper separation of concerns. One of the first things that happens when a droplet boots up is the Nitro security chip goes and does a lot of measurements to check that the firmware it's running is as expected. And if it's not, that droplet gets taken out of service and we'll deal with it later on at some point. We'll move on to the next droplet and we'll just continue from that. The Nitro controller will also start measuring itself. Even when the droplet's up and running, it'll just continue measuring itself, and then the same process occurs. If there's any issues where we think actually for a second that doesn't look quite right, we take the whole droplet out of service, put it to one side. Instances get shifted if we can't fix a problem quickly enough, which is a matter of nano or microseconds, and then life continues and we look at that droplet another time. Now, one thing it allows us to do is, if we've got a lightweight hypervisor, is we can do live updates of software, including the hypervisor, without any downtime. So we can do firmware updates on the fly, even though your instances are running on top of them, which is a bit of a strange concept. It's like changing the car fundamentally as you're driving down the road while you're still driving at about 170 miles an hour. So that software that we do with the hypervisor is developed by teams across the world. So we have a globally distributed team all around the world. That's a common Amazon thing to do, but the specific advantage here is that fundamentally we're solving two main problems there. One, we are solving a nation-state interest problem. Certain areas of the world can't be less interested or more interested than others because there's lots of people involved. But the second thing we do is we provide the ability for engineering staff to be available practically 24/7 when there's a need to have an issue occurs or there's a need to fix something or whatever it might be. We cryptographically sign every single firmware update that goes into the Nitro hypervisor. That's done automatically, gets cryptographically signed, and that signature is checked when we boot up a host. And we deploy it all through EC2. So the actual thing, essentially the whole thing's dog fooded is the way to think about it. EC2 manages EC2 at this point. So we deploy a new version of the hypervisor, that goes through a pipeline which runs on EC2, that gets deployed through EC2 back onto the instances themselves through EC2. And that's how we end up there. Big one here, no remote access. There is no SSH server. There is no access to SSH in any way, shape, or form. There's no way to get onto those droplets unless you go via the Nitro cards and the Nitro controllers. And they have very few APIs, and those APIs are very tightly scoped into doing things. I have lost my mouse somewhere. There we go. The APIs that they do have, however, are encrypted, authenticated, authorized, and logged. So we know exactly what's happened and which systems have talked to those other systems. We have logs to prove it and all the rest of it. But the big thing, or one big thing about that, is that none of those APIs also expose a way to access any customer data or instance or anything like that. So they are purely able to talk to the Nitro hypervisor. The hypervisor is then in control of the rest of the stuff, but the hypervisor is very lightweight, so it can't do an awful lot in the first place, so on and so forth. So effectively, the security chip provides us with fully encrypted communication channels, cryptographic verification on boot. We can update without downtime, and we have absolutely no remote access, which is good for you. Back to confidential computing. What we have here now is a situation, a new dimension's occurred. Okay, there is more than one, fair enough. We have a situation here where in the second dimension down the bottom, we are now able to separate the idea of, or would like to be able to separate the idea of customer data on an instance from the sort of highly sensitive customer data that exists there. To give you an example, you might consider, for example, a key material to be more highly sensitive than an application that runs there, for example. So you might want to separate those things out on the same instance, because at the end of the day, the instance is the lowest building block you've pretty much got in EC2. You still need the instance to see the key. You need the key to be kept locally to the application. You don't want to transfer over the network for a variety of other security reasons. So how do we do it? Well, we built a thing called enclaves or Nitro enclaves. Nitro enclaves are effectively fully isolated compute environments that live inside or connected effectively to an EC2 instance via a local socket. So there is no remote access to them at all over the network. You have to connect them, and a local socket is exposed for access to the Nitro enclave. Gives us a couple of advantages. Firstly, the enclave itself is very hardened and completely isolated. It can do not an awful lot. You can only access it through a secure socket. The second part is that it has attestation, which goes through KMS. So therefore, we're saying that the sensitive data that you've got, once you've defined what your sensitive data is, you do that by saying this is what sensitive data looks like, but not what sensitive data is. Then KMS manages all that and works all that stuff out. And the advantage of KMS is doing it is you get all the KMS goodness for that process as well. You have to redo everything. And use cases, generally speaking, PII, healthcare, financial data, really straightforward ones, encryption keys. There are use cases out there. Lots of people got really excited about Nitro enclaves when they first came out and then couldn't find a use case for them. I think I have single-digit number of customers who have a use case, and even a fraction of those have them in production. But for when you need them, they're incredibly useful because they provide effectively guarantees that say you cannot get to this stuff. It is in the most desolate, isolated section of compute we can possibly provide, and you're in full control of them as well. Another thing we got to do through Nitro and by splitting things out was UEFI Secure Boot. This exists in lots of different ways on machines you can get physically. Didn't exist in the cloud at the time, and effectively ensures that the bootloader is properly signed by a known authority. So you're basically turning around and going, my instance can boot up as long as it's cryptographically signed by a certificate authority I trust in the first place. If I don't trust a CA, or the certificate that's presented when we're trying to boot up is not from a known CA, we can kill the whole thing off and not boot the instance, error out, and everything's fine until we can fix the key problem. People have UEFI Secure Boot on-prem and have had for donkey's years, and they really wanted it in the cloud. It was a bit of a challenge to do. If you're a Linux user or you've tried to manage things on-prem, you'll probably have come across the delights of Grub2 in the past, which manages all this stuff for you on-prem. You can run Grub2 in AWS as well, or you can just tick the box that says I'd like to use UEFI Secure Boot, and we'll do it for you with or possibly without Grub2. Yeah, so that's the advantage we get there. People wanted it because they had it on-prem, now they can get it in the cloud. You also got a fallback here, which is you can fall back to backup bootloaders. If you can't boot your instance in the way you're expecting because of a certificate chain problem, you can turn around and go, I either want to use a different bootloader entirely and I'll boot this instance up effectively as a different instance, or I'll just stop and we'll work out what to do manually at that point. So fundamentally, if you have an instance that needs to only boot up once that instance's AMI is signed by a cryptographic key that you trust, then UEFI Secure Boot works through Nitro. We also have people who wanted a TPM or a Trusted Platform Module. Trusted Platform Modules effectively say that they effectively provide a separate hardware root of trust at a low level. So there are a variety of use cases for them, mostly to do with confidential and secure computing. There's an industry standard out there called imaginatively TPM2. There was a TPM1, there might be a TPM3. Today's is TPM2. And effectively, it has software compatibility with a wide variety of bits of software that people already use, like BitLocker, for example, in the Microsoft world, that enables people to actually make use of a TPM without having to interface with the TPM directly. So it just looks like a hardware TPM to an EC2 instance that uses it. So all that software works. And then you can do things like, have attestable system state, generate cryptographic data on the fly in the TPM, store it in there, prove platform identity. So are you running in AWS or is someone lying to you? That's for some customers a genuine concern. You can do all that through there. You can get access to make things like LUKS for file systems work. All that stuff now magically works nicely because of a TPM, which runs on the Nitro security chip, which we talked about earlier on. You can read an awful lot more about this. There is a whole PDF about this sort of stuff. I have tried to whittle down the fun and interesting features, but if you want to, there's a nice QR code there. 2 people have held their phone up. I now feel great. Thank you. Not that it's a competition, but you can read that if you want to. And we had NCC group go through the AWS Nitro system to work out, does it say what it does on the tin? And they said yes. And if you want to see that and read it, you can read it there. It goes into also the things like integrity protection, tenant isolation modes, no operator access design, and a wide variety of other things that we talked about. And it's available online. There are probably there may well be a newer version, but it hasn't changed fundamentally since 2022. It's been working fine for the past nearly 3 years, and before, because it's been around since then, since at least before then. Yeah, if you want to read it, it's on the internet. Right, I want to talk a little bit more about how our hardware works behind the scenes. So that's all the software goodness and stuff, but we'll talk a bit more about the hardware to put it all together as a end-to-end, how would this work? So, today, a droplet. If you go into our data centers and you pull out a droplet from a rack, you will get something that looks like that. There's millions of things. They produce noise. It is very noisy, all that sort of stuff. That is where your EC2 instances and everything else you practically run in AWS exists at some point on that sort of stuff. This in particular is a Graviton 3 droplet. So it has a Graviton 3 chipset in there, and it has the Nitro system running on it as well. There are 3 non-coherent sockets towards the front. You can see them. There's those 3 sort of rectangles that are effectively exactly the same. They can either host 3 bare metal instances. So in bare metal, we have the problem of you can have a bare metal instance, but we can only run your operating system on that entire section of the droplet. And as a result, you will pay more for it because scale means that we can't have lots of those flying around for dirt cheap. Or we can host many EC2 instances, or even many more Firecracker instances on there. And there's a whole life cycle that's basically entirely decoupled from everything else in there as well. So that's how that looks and operates, and that's what it is on there. Now, on the left-hand side, I want to put all this together and try and explain to you how an EC2 instance launches, which I think is correct, but we shall see. I might prove myself wrong in a second. You as a person, as a user of AWS, send your request and it goes through IAM, and IAM does all its stuff with the security token service and checks that your SIGV4 token is correct and all the rest of it. That's off to the left-hand side of this diagram. We're going to assume by this point that that is fine. We're going to say that that is fine. We've authenticated that this user is allowed to do this action. IAM has said, yep, absolutely fine. We're going to go and start to do the action. The request comes, once that's happened, the request comes straight into the EC2 control plane on the left-hand side. And the EC2 control plane effectively runs a large number of services that together make up EC2 and control things going on. 99.999% of those services are not exposed to you, have frankly no real reason to exist other than service your EC2 instance requests in the first place, and are completely our responsibility. So I'm not going to go into what they are, even though some of them are really interesting. You'll just have to maybe find out about those one day in future. The EC2 control plane, however, needs to talk, firstly, takes your request in, and it needs to talk over an API. It needs to talk over an API to a Nitro controller, because that's the interface from the outside of that droplet from the previous slide with the EC2 control plane. But we're not going to have a communication over an API that's not authenticated, not encrypted, and not authorized and not logged, which is the last bit I missed off there. So, let's see. In the very first instance then, the EC2 instance talks to the control plane talks to the Nitro controller and effectively says, can you allocate me some resources on a Nitro droplet? I don't really care less where it is, just these are the constraints you've got based on the request. Give me some CPU memory, get on with it, tell me when you got them. A Nitro controller goes and decides which of the hypervisors available to it on that droplet it's going to choose to allocate resources on. Now you might think, hang on a second, how did we get from the big control plane over here to one specific droplet? There's a scheduling service for that. There's a whole control system for that to work out where it's going based on differences in the request and capacity and all the rest of it. We're going to assume that's already happened here for sake of argument. We've gone here to the Nitro controller specifically on a droplet we've been specifically told to use. So the controller's gone to the hypervisor and it said, can you reserve me the CPU and memory? This is what I need. This is what I've told the control plane I can have. Please make it work. Hopefully it does. Please don't tell me you can't have them, because if I do, it's embarrassing. And it goes, sure. There you go. There's some CPU and some memory. And so we therefore have the very first baked part of our Nitro instance. That's how we create your EC2 instance in the first place. That's what's going on. And we've already really got there is CPU and memory. There's nothing else there. So we have no network access, no storage, no operating system. There's absolutely nothing on that. It's completely useless to use an instance. But from this moment on, your instance starts to exist. This is the birth of an instance, if you will. Now, when everything's set up on the EC2 control plane and in the Nitro host, then what happens is we go to the Nitro cards and say, please, can you start to do your magic and allocate things like EBS storage access and network access and stuff in line with the parameters in the context you're running in. So an EC2 instance in the VPC, for example, will turn around and go, I am from this account, I'm from this VPC, I know all this stuff about where I should be running. Based on all that information, can you allocate me resources and give me access to things I should have automatically, and then make changes to things I need to have to get for those things to occur. So that gives us our root volume effectively and a network interface, so we can start to actually talk to the instance in the first place. So for the first few seconds of running an EC2 instance, the thing is completely isolated from you. You can't talk to, you can do nothing. You've got to wait until it's available. So you'll see the little spinny the new UI doesn't show you that, but the old UI had the little spinny dots that went round and round and round. That was effectively what was starting to begin with. Then we get our three main things there. We get networking, security advantages, we get our EBS, and we get our local storage available to us. And then we go back and we effectively do the same things for all the other cards and say, can you just make sure all these things work and talk to things and provide connectivity and all the rest of it. And at this point, we're then at the point where we can start to say, well, can you start to direct the I/O requests that we need effectively? In short, the requests we got so far are only to get this base layer of stuff to work. We now need to put an operating system on there so the instance is usable for you. We can only do that once we got this sort of stuff working in the first place. So the OS goes on there, and the control plane goes to the controller and says, right, can you make that instance available? Tell me if it's available or not. Give me an update on it. If it's available and the OS has started to install and it's bootable and we think it's good to go, then I can then tell the user all is good. I can respond to the request, and away we go. So that's how that works. That's for a C7G16 large. It could be exactly the same for a whatever other instance type you want to run on Nitro. They all work basically exactly the same way. Some won't. If you've gone for a bare metal instance, they'll be ever so slightly different, but the core fundamentals of how an EC2 instance is birthed in the first place are basically that. And we do that thousands and thousands and thousands of times every 10 seconds. That happens all the time, 24/7 around the world, unless it's a Monday, in which case it doesn't. Finally, we install our OS, and that's our instance ready to boot and good to go and ready to use. And we do that on the other host, on the other instances on there, so we can have more instances on the other host inside that droplet. We can do it simultaneously. We will do it simultaneously. We may not bin pack instances onto droplets in order. We may randomly allocate them all over the place, but fundamentally we can have this happening lots of times. It will be happening right now, lots of times simultaneously, even on the same bit of hardware. Now, the nice advantage of that is it can do that because fundamentally we're managing most of this stuff on the Nitro cards, which have their own isolated bits of compute to do this sort of stuff in the first place. If we're waiting for shared CPU, you would be in a long line of people waiting for your that droplet to allocate resources for everybody else's EC2 instances first before it got to you, which is really inefficient when we turn around and talk about on-demand scalable computing. So, one of my favorite features is that Nitro allows us to do weird and wonderful things like bring macOS to EC2. And the way this works fundamentally is we wanted to turn around, we had customers turning around and saying, I really want to build iOS, tvOS, watchOS, whatever other OS they're going to come out with applications, macOS applications in future. But in order to do that, I need to run on Mac OS. Now, you have two main ways before this of doing that. One is you go down the Apple Store and you buy a boatload of Mac Minis. And two, you go to an organization that did exist, they probably still do, that has done that on your behalf and will sell you effectively virtual access to those over RDP or whatever, or VNC, whatever protocol you wanted to use. Right? So there were data centers in the London area full of people who had Mac Minis just stacked on top of each other. If you look at the original or the more modern Pixar render farms, rooms and rooms and rooms and rooms and rooms of Mac Minis. And it's just really inefficient because Apple doesn't let you take the things apart. If you do, the whole thing doesn't work. So you've just got hundreds of Mac Minis on top of each other. We were like, well, given we can run a bare metal instance now on Nitro, can we just take Mac OS and run it natively and as a bare metal? And two problems there. Firstly, no, you can't, that doesn't work, it turns out. And secondly, even if it did work, that's still fairly expensive to do because we've now, for each droplet that can hold, say, 3 instances, I've now only got the ability to, on that droplet, to hold 3 Mac OS EC2 instances rather than the hundreds I could possibly otherwise hold. So we decided, how do we do this? Well, nice and simple. We make a sled. We put a Mac Mini in it. We expose PCI, or Thunderbolt in this case, because Thunderbolt and PCI are from memory not too different. And we connect the Nitro cards, the Nitro security chip, and the Nitro controller into it. And I've not got a picture because, unfortunately, well, I do have a picture, I just can't show it you. But if you look at these things, it looks like a Mac Mini mounted on a sled. And they just slide into a droplet. And that becomes a droplet, and we have hundreds of those, thousands of those, whatever we're up to nowadays in our data centers. The advantage of that is, fundamentally, we can give you the elasticity, the security, and the reliability that Nitro provides to you, which we've discussed so far. With Mac OS AMIs, we can use EBS volumes for boots rather than having to have APFS from memory in the Apple world. And we can also provide things like VPC security groups, CloudWatch metrics, and all the things you like in the cloud. So you can get all that stuff out the back of a Mac as well. So yeah, if you open up the tin, the lid effectively of Mac on EC2, there's a Mac Mini sat there. That's all it is. We've just basically been to the big Apple store for you. Yeah. So, in short, thank you very much. That was a very brief run through, I think, of how we do our stuff. I will hang around for a bit for questions, probably till about 9ish. And then, yeah, that's me. Thank you.
Thank you, Andrew. Thanks for that.
No, yeah, good idea.